Hello everyone, I am Dr. P. Rajkumar, Assistant Professor, Department of Mechanical Engineering. Welcome to Machine Design course. The topic for today's discussion is design of eccentrically loaded welded joints. So at the end of this session you will be able to understand how to design the welded joints for the eccentric loading conditions. So we already know that the welded joints are of two types, like parallel fillet and the transfer fillet. So as a case 1 we will be seeing how to design the welded joints, eccentrically loaded welded joints, transverse welded joints. So if you see here, it is like T joint. It is a T joint and it is subjected to the load of P at a distance from this edge. The distance is E. So this welding is subjected to the eccentric loading at a distance of E, and the applied load is the P. S is the leg size, L is the length of the weld. So here the T indicates the throat thickness. You have seen in the previous session that how to calculate the T, throat thickness value, how to calculate, and how to calculate the weld area also we have seen. Now in this case it is a double transverse fillet weld. So now as a case 1 what we are seeing, we are going to see how to design a double transverse fillet weld subjected to eccentric loading. So we know that the area, how we can calculate the area is nothing but, weld area is nothing but throat thickness into L value. So T is nothing but, it is given by 2 times because double transverse. So 2 into T into L. This throat thickness value is given by 0.77. Yes, S is nothing but your leg size or weld size. So this one A you will get it, and because of this one, because of this applied load P, the first one you will get the direct shear stress, and second one you will get the, because of P into E distance you will get the bending moment. So because of this eccentric loading, what are the 2 kinds of scenario that is occurring? First one is because of this point load you will get the shear stress, and because of this P into E distance you will get the bending moment. So now coming to the, because of the first P you will get the shear stress. So shear stress is nothing but your load per unit area. So you have already calculated the unit area. Now we have to calculate the P value. So that is tau is equal to P by A. You will substitute A value, you will get the, if tau is given you can calculate P, if P is given you can calculate the allowable shear stress. Both the things you can do it. Now coming to the section modulus we have to calculate, because we know that the bending stress developed inside the welded joint is given by sigma B is equal to M by Z. Z is nothing but I by Y. Z is nothing but, your Z is nothing but I by Y. Here I is nothing but your moment of inertia. Moment of inertia, Y is nothing but here your thickness by 2. You will get it. Throat thickness, you will get, throat thickness by 2 you will get is BDQ by Z value for a rectangular cross section. You will get I value is BDQ by 12. So by substituting all the values in the, I value is BDQ by 12. So you substitute that value in that I value, and Y is equal to value substitute, you will get the Z value. So Z value you are getting 2T into L square by 6. You will get it. So how you are getting this value? So here it is nothing but T, what is this length? This is L, so T into L cube by 12, Y is nothing but L by 2. So 2, 6, L gone. So we will get T L square by 6. So that is what you got it here, the Z value. Since it is a double transverse, it is into 2. So substitute this Z value here in this equation, you will get the bending stress. So what is the bending stress? Here you are getting 4.24 into P into eccentric distance by S into L square. S is the leg size, L is the width, your length of the weld. S is nothing but size of the weld. So this is the case 1. It is subjected, nothing but same thing only, transverse. It is direct shear stress, another is the bending moment. So this load, because of this load, direct shear and the bending moment we are getting. Once you get both the values, once you get the sigma b and you will get the tau value, then you can use the theories of failures to calculate the equivalent stress. So according to the maximum normal stress, you can calculate sigma T max is equal to sigma b by 2 plus half into under root sigma b square plus 4 tau square. So by substituting all the values in these given equations, you will get the sigma T. So if the stresses developed inside the welded joints is less than the allowable values, then we can say the welded joint is safe. If it is exceeding means, then the welded joint will fail for strength criteria. So this is according to maximum principal stress theory, and this is according to maximum shear stress theory. So you can use any of the theory to evaluate or to find out your final parameters. This is case 1, design of double transverse welded joint subjected to the eccentric loading. Now coming to the second loading conditions. The second loading condition is design of parallel fillet weld subjected to eccentric loading. Here now you can observe these are the two parallel fillet welds, and you know that because of this applied eccentric load P at G is nothing but it is a location of the throat thickness center of gravity. G indicates throat thickness center of gravity. So because of this P, now what I am trying to do is I am trying to take P1 is equal to P2, two loads such a way that P1 is equal to P2. So because of this P2, you will get the direct primary stresses, you will get it. Because of this P1 you are getting the direct shear stress, and because of this P2 loading, you are getting shear stress due to turning moment. Because this P1 is equal to P2 is equal to P. So P into this radial distance will give you the turning moment. So the shear stress due to turning moment. Because of this turning moment, you will get the shear stresses developed inside the welded joints. So now let's see how to calculate the primary shear stress and the secondary shear stress, and how to calculate the resultant stress developed inside the welded joints. So the primary shear stress, here you can see the load per unit area. So the load applied is P, per unit area you know T into L, since it is a 2 times, so 2 into T into L. By substituting that one, you will get the primary stress, shear stress developed inside the welded joints. But in the secondary stress, as I already told you, the secondary stress tau 2 generated inside the weld cross section, which is at a distance of R2 from the center of gravity of the your throat, it will be perpendicular. From this, it is proportional to the radial distance, this R2 distance. So from this equation we can write T by J is equal to tau by R. From this equation I can write this tau by R value is constant. Tau by R value is constant. Because the secondary shear stresses developed at any section is directly proportional to the distance of throat to that weld cross section. So that is what we have written here. And by substituting the remaining all the other values, J value and twisting moment values in the T by J equal to tau by R value, you will get the tau 2 value. Tau 2 value as T into R2 by J. J is nothing but polar moment of inertia for a weld sections. So by substituting this tau 2 value in the given equation, you will get the tau 2 value, tau 1 value we already know. Once tau 1 and tau 2, since both are same category, tau 1 and tau 2 both are belongs to shear stress category, we can use the resultant equations. It is nothing but we have seen the resultant equation how we used to calculate p square plus q square plus 2pq cos theta. This how we used to calculate. One is p, one is q here. So the resultant we can use to calculate. So similar way, tau 1 is there, tau 2 is there. So using these two we can calculate the now resultant shear stress. So as I already told you, the resultant shear stress tau A is equal to under root tau 1 square plus tau 2 square plus 2 tau 1 tau 2 into cos theta. Tau 1 is primary shear stress, tau 2 is secondary shear stress. And this theta is given by the distance between, the theta is the ratio of R1 to the R2. Cos theta is okay. So by substituting this value you will get here the resultant shear stress tau A you can calculate by substituting tau 1 value and tau 2 values in these equations. So theta, how you will get it? The theta is nothing but it is the angle between your primary shear stress and the secondary shear stress. So between these two you can calculate the tau value. And how to calculate this R2 value? R2 is nothing but your, if you treat this as a one right angle triangle, so it is R1 square plus under root of your A to this distance. This is half of the distance, that means B by 2. B by 2 distance you will get it. R1 square plus R2, R1 square plus B by 2 whole square under root. Then you will get the R2 value. So as I already told, the parallel fillet welds is subjected to eccentric loading. Because of this, what are the we are getting? Because of the first one, the primary shear stress, and because of this P into E effect, we are getting the secondary shear stress. So tau 2 are known as the secondary shear stress, and tau 1 is known as the primary shear stress. So by using parallelogram theory, tau 1 is the primary, tau 2 is the secondary. You can calculate the resultant shear stress. So let's see one problem on this. A welded joint as shown in the figure is subjected to an eccentric load of 2 kilonewtons. Now they are asking you to find the size of the weld if the maximum shear stress in the weld is 25 megapascals. They have given the maximum allowable. Since it is a double transverse, so we will get the area is nothing but 2 times T into L. T is nothing but 0.707 into S into L. S is, this is the size of the weld. Size of the weld, that's what they are asking you to calculate. So by substituting all the values in the A value, we will get this one. So now how to calculate? This is the case 1 criteria. So we can use either maximum principal stress theory or maximum shear stress theory to calculate this size of the weld. So the first shear stress I am calculating, tau is equal to load per unit area. So you will get equations. Then bending moment P into E, by substituting this Z value and the M value in the sigma B is equal to M by Z, you will get the sigma B. Once you will get the both tau as well as the sigma B, you can use the maximum principal stress theory, that is, or shear stress theory. So since they have given the allowable maximum tau max value, they have given, we are using the maximum shear stress theory value. Maximum shear stress theory where we are using. So tau max is equal to half under root sigma B square plus 4 tau square will give you the maximum shear stress in the welded joints. So since this value is given, sigma B only unknown is a S, tau also only unknown is a S. So like that you can calculate the size of the welds whenever a welded joint is subjected to the eccentric loading. and this is case with the parallel fillet welds subjected to the eccentric loading. So R1 this value, and R2 we can calculate under root of this value plus under root of this value. Polar moment of inertia for this parallel fillet welds, this is the standard formula. You can access this formula from the design data book. So this is the polar moment inertia formula you can take in, and tau 2 value directly from the previous derivations, P into E into R2 by J. J is just now equations we have seen. R2 is nothing but, I already told you, R2 is nothing but your R1 square plus under root of half of this width, that means 40 square. Then you will get this R2 value, AG value. So by substituting that R2, you will get the tau 2 value also. So cos theta, we know that it is cos theta is equal to R1 by R2. So that is also calculated. So substitute tau 1 value, tau 2 value, cos theta value in the final resultant shear stress equations. So from that equations you can calculate the size of the weld. So these are the axially loaded unsymmetric welded sections. Till now we have seen the length of the welds are equal in both the sides of the neutral axis or gravity axis. But here there is one more category where the length of the welds is not same. So in those cases, how to calculate the length? LA is given by L. L is nothing but the total length. That means LA plus LB will give you the L. So how to calculate LA? LA is equal to L into B by A plus B. LB is equal to A by A plus B. That is how you have to consider for a axially loaded unsymmetrical welded sections design parameters. These are the two equations you can use while designing the axially loaded welded joints. So this is the small problem on that equations, and these are the different textbooks you can use for the further reading. Thank you.